Hey everybody. I've had a few people ask me about solutions for homework number 5, and I figured I would just put out a video and kind of talk through what you were supposed to do for all of these problems, uh, and hopefully this allows everybody to make sure that they're on the right track as they go through and prepare for the exam. So let's get started here. Just to warn you, I have the tablet with me, but I forgot the stylus. I feel ridiculous saying Apple Pencil, but so I'm just going to use my fingers, or I guess just one finger, if I need to make a diagram. So it might not be as nice as normal, and you might argue that they aren't even normally nice, but I'm just going to do the best that I can, all right? Okay, so for this first one here, we don't actually need to make a figure, I think, so we can just get through this without too much of a struggle. So let's go through and just say what everything is. We have delta t is 5 seconds, and delta theta is 25 radians. And that's all we're given here, actually. Okay, so I think that the way to go about this is actually to do part B first. And so let me say that or by definition, the average angular, I'm going to say speeds here because it doesn't really matter. We don't know exactly which way this thing is spinning, right? Whether it's counterclockwise or clockwise, so we can just keep it general. We don't have to assume anything. And so this would be my angular speed, or my average angular speed. I'm going to put a bar over it just to make sure it's clear that this is an average. And remember that this is just delta theta over delta t. And that's it for this part, right? So you would just divide 25 radians by 5 seconds, and you should find that it's 5 radians per second here. Okay, cool. So let's look at A then, because I think for A, if I'm not mistaken, we have to be a little more careful with our approach here. Let me say recall that, again, by definition, the average angular speed is given by the initial angular speed plus the final divided by 2. And remember here actually that omega initial, because this thing starts from rest, is just 0, right? So I could just put a line through that because it's 0, and we have that this tells us that omega is 2 omega bar. And let me just okay, so I was confusing myself a little bit because of the example problem that I did in the other video, but this is good. So, okay, so omega final is just 2 omega bar, right? Which of course is just 2 delta theta over delta t. Okay, so then we can apply another equation, right? Remember, one of our equations was that omega equals omega initial plus alpha delta t. And this omega naught is the same as the other one, so this is also 0, right? And so what we have is we have that alpha equals omega, oops, I wrote a W, doing that a lot lately. Alpha is simply omega divided by delta t, right? Now, remember that omega is 2 omega bar divided by delta t. So there we go, and let's see here. Well, you could get an answer with this, right? Because we already know that omega bar is 5 radians per second. And so that, I think, is all good. Though if you want to work symbolically, right, like you remember that your final answer should only depend on things that you were given, so you would just substitute in that omega bar is delta theta over delta t, right? Let me just make sure that everything here looks good. Yeah, I think this all looks fine. Okay, so now that we have, right, with the angular acceleration in hand, we can figure out that, or we can simply write that for part C here, that omega at 5 seconds is just omega naught plus alpha. Jeez. There we go. Delta t. And actually this does look a little confusing because here, right, I'm saying that this is alpha times delta t, but this is omega at, so let me make this maybe a little bit clearer. I'm going to write omega at t equals delta t. Okay, hopefully that is good. And then we have alpha from the previous part, and we know delta t is just the 5 seconds. So this will give you the answer for C. And so for part D, we just need to, what do we need to do here? The angular acceleration remains constant through how many more radians will the disk turn in an additional 5 seconds? We need to apply this equation. Right, the one of this form, and so I want to use maybe capital theta here for the other angular displacement, the number of radians that the disk turns through in an additional 5 seconds, and we just apply this equation, but because we're asked how many more radians, we can just take theta not to be 0, right, because we want to solve for the number of radians above and beyond the 25 radians that we're given in the problem statement. Now, omega naught in this case, so the omega initial for this part of the problem is the omega final from the other part of the problem, right? So that would be the 10 radians per second. I'm just going to call it omega. And then we have here that the time interval is delta t again, right? And then plus 1/2 alpha delta t squared, okay? And delta t is just 5 seconds. Omega is going to be, it looks like, 10 radians per second, right? Because it's double the average angular speed from part B. And then alpha is constant, right? So it's just what we found for part A, this result here. So this is how you would do this. Okay, cool. So let's look at number 2 here. And for number 2, I'm gonna have to make a crappy sketch. What's up, dude? With my finger, because as I mentioned, I forgot the stylus. So let's see how this goes. So for the first one, right, this might look a little bit complicated, but it's actually not so bad once you recognize the symmetry that is involved here. So we just have two masses, right, of 1/10 of a kilogram, and we have that, let's see here, all right, plus or minus r for the position vector of the masses. Or maybe what I want to do is I want to write r sub plus or minus. That's probably better. And I don't think you can see the minus sign, it's hidden. Also, I'll just do plus or minus r. And this is going to be, let's see here, plus or minus out in front, 0.3 meters, sorry, negative 0.3 meters, and then 0.3 meters, like this. Or, you know what, I'm sorry, this is probably confusing. Let me just do this. It's the simplest way, I think, which would be r sub plus will be negative 0.3 meters. And this is, of course, a vector. And then r sub minus is going to be 0.3, negative 0.3 meters. Okay. I think this is the best way to do this. So let's just make a very quick sketch of what this looks like. And so what we have, right, is we have our x and y axes, x and y, and then we want to put in the line y equals x, which just looks like this, of course. It's just a diagonal line with slope of positive 1. And one of the masses is going to be, say, here, and the other is going to be here. The one up top, so the one in the second quadrant would be r plus, right? Its position vector would be r sub plus, and the one in the fourth quadrant would be position vector r sub minus, I think, as I've written this. Now, remember that we want to figure out what the perpendicular distance is from the axis of rotation to the object with the mass that's contributing to our moment of inertia. And so, wow, that was bad. Let's see if I can erase that. Cool. Try this one more time. So the position vector, oops, undo that, okay. I think we're, geez. Okay. The position vector would look like that, right? And then this position vector would look like this. So we see that these are already, these distances corresponding to these vectors are already perpendicular distances from our axis of rotation, right? And so, also by the symmetry, right, if we figure out what the moment of inertia is from one of these, we can just double it, because this is a sort of a perfectly symmetric setup we have here. So we could say that the total moment of inertia is just two times m r sub plus squared, right? It doesn't matter if we use r sub plus or r sub minus because of the symmetry here. So this is just going to be 2 times 0.1 kilograms. And then we would use the Pythagorean theorem to figure out what r sub plus is, or r sub plus squared, right? And that's going to be simply negative 0.3 meters squared plus 0.3 meters squared. And then whatever this works out to be is your answer, right? So when you're doing moment of inertia calculations, you want to be on the lookout for symmetries that you can exploit to make the calculation easier, and I think that every one of these problems that I gave you actually has a symmetry that you can use. So that's that. Now we're going to look at the other one, and this is probably going to be a little rough because I have to draw with my finger, right? But I think we'll get through it. So the way you could visualize this, I realize I'm not sharing the tablet, so just let me draw this and then I'll share. Okay, not terrible. Would be like this, right? Now this has radius r, and the sticks have length L, and our axis of rotation, right, according to the verbiage of the problem statement, is like this dotted line here. And again, right, the endpoints of the rods are both a distance r from the axis of rotation, and the rods are the same rod, right? They have the same mass and the same length, so all we need to do is figure out what the moment of inertia of one of these rods is, and then double it, and that will account for the contribution of the rods to the total moment of inertia here. So let's do this. What did we say it was? It was a solid sphere, right? And so we can write that the moment of inertia of the sphere is going to be 2/5 mr squared, right? And the total moment of inertia is just the moment of inertia of the sphere. Remember that we have a ready-made formula for this moment of inertia of the sphere, right? It was in the table I gave you during the lecture. And then we just have to figure out what the contribution is from the rod, from one of the rods, and double it, right? So this is our expression for the total moment of inertia here. Now we know that this is at 2/5 mr squared times the moment of inertia of the rod. Then we have to use the parallel axis theorem, right, for the moment of inertia of the rod. And remember that we have to start with the moment of inertia of the rod about its center of mass, which should be 1/12 ml squared, and then we have to do plus the mass of the rod times the distance from the axis of rotation passing through the center of mass to the new axis of rotation, right? And if you look at the sketch, I think you can convince yourself that this is just going to be big R plus L over 2, and then we have to remember to square this, right? And so you can go through and you can you know, expand this out, see if it simplifies or anything like that. And I mean, I personally would never do this by hand. Of course, I'd make Mathematica do it, but this is what you should have found, something like this, right? Let me just make sure that this checks out. Yeah, I think this is good. Okay, so this would be your answer for B. Now let's look at C. And again, we're going to have some symmetry here, right? Because, let me make a sketch, and I'll show you what I mean. That's kind of terrible. We'll try this one more time. Okay, it's a little better. So a very, you know, crappy sketch of this could look like this, right? Our axis of rotation is given by the dotted line, and then we have two spheres. They're only touching at one point. It doesn't look like they're touching at all in my sketch, but that's because, again, I'm drawing with my finger, right? But this is just a matter of basically thinking about what the moment of inertia of one of these would be. Let's focus on the right one, maybe through an axis passing through its center of mass, then figuring out the moment of inertia through the axis represented by the black dashed line here. And then once we've done that for one, for the total moment of inertia, we can just double that result, right? Because we have two identical objects here. So let's work this out. Hang on. Okay, so let me just say for one of the spheres, moment of inertia from the parallel axis theorem is going to be, remember we start with the moment of inertia about the center, or about an axis passing through the center of mass, and so for a hollow sphere or a spherical shell, it's 2/3 m r squared, right, plus the parallel axis term, right, and in this case we're just actually moving the axis of rotation by a distance r. And I think if you look at the sketch, you can see how that makes sense. And so this is the moment of inertia for one of the spheres, right? One of the hollow spheres. Now the total moment of inertia is just 2 times one of the moments of inertia. So you should find that it's 2 times this. And you can combine this, right? What would this be? This would be 2/3 mr squared plus 3/3 mr squared. So this would be 5/3 mr squared, right? So you should find that, and don't trust my ability to add fractions in my head, double check that, but the idea is good. Now this should be 2/3, or that 2 times 5/3 big M big R squared, like that. So it looks like it should be 10/3 mr squared. Okay, cool. So now we're going to look at number 3, and this is going to be probably a little bit rough because this is one of the ones where it's very critical to draw a good sketch, but I will do my best. Let's see here. Okay, so far not so bad. And I need to put the forces in. Okay, it's actually looking a little awful when I try to write with my finger. And I realize that you can't see this, I'll share my screen in a minute here. I don't want to put the angle in too. This is theta. Okay, so this is the sketch. It should look something like this. Now, we don't know where the person is going to wind up, right? And remember, the person's gravitational force is represented by little mg. So we just draw it in somewhere, right? It doesn't matter because we'll see that no matter where it's orient or where it's located, its contribution to the torque is going to be such that it would make the ladder rotate clockwise, right? If we take our axis of rotation to be here. Okay, so this is the picture we want to have in mind. Now, what we do here is we just go through and we sum our forces in the x and y directions. We'll do this first because I think it's a little bit simpler. So let's say sigma F in the x direction is going to be just the friction force minus the normal force from the wall, right? And static equilibrium, this is 0. Okay, we'll do the y direction. And we're going to have big N minus big mg minus little mg equals 0. Remember, because the ladder has mass here, so we have to remember to account for that. And then the torque is going to be a little bit trickier. Remember we said that our axis of rotation is going to be here, right? So that means that this normal force, the one from the ground, and the friction force don't contribute to our torque, which is good. So you don't have to worry about those. Now, let's see. Actually, I need the picture one more time. we need to make sure that we're good on the angles. And so let's do this. Let's make perpendicular lines from the ladder. Why won't you? Oh, because you're writing with my knuckle. Okay, so there's this one, there's this one, and then there's this one. And remember that we're doing this because we want to figure out what the perpendicular component of each of these forces is, right? And when I say perpendicular component, I mean the component that's perpendicular to the axis of the ladder. And so we need to get a good idea of the geometry here. Now, what I want to say is that, let's see here. This angle is theta, and this angle is theta, right? Now, this angle here, stop it. This is theta also, right? So what that means is that this angle here has to be phi, right? And if theta is 30 degrees, then phi is 60 degrees. Because we would have a right angle between this dashed line and this dashed line, right? So we can see that phi must be 60 degrees. And you could use theta here too, it doesn't matter, right? Because you can use just the other trig function, you know, let's say sine or cosine to get the component, but I'm going to use phi. Okay, so let's do this then. Remember that the forces from the weight of the ladder and the person will tend to make this ladder rotate clockwise about our chosen axis of rotation. And so what that means is that they should be negative, or the torques corresponding to them should be negative. And remembering that the center of mass of the ladder should just be halfway along its length, we can think that the gravitational force is acting at that specific point, right? And we want the perpendicular component here, so we have to add on cosine theta. Yeah, I think that looks good. And then we do the same thing for the person, right? mg, and we'll call the length along the ladder that the person can go script L, right? So this script L is the distance along the axis of the ladder. And then we also have to tack on a cosine of theta here. Now, the normal force from the wall, right, if you think about it, would tend to make the ladder rotate counterclockwise. So it would be positive. And we have n cosine phi, it looks like, right? But you could also write sine theta here if you wanted to. Maybe I'll do that because that would, you know, I think simplify things a little bit. Okay, so we have this stuff now, right? And I'm not going to belabor this too much, but remember that the friction force, the maximum static friction force, right, is going to be given by the coefficient here times the normal force, and we have to choose the correct normal force. And since, looking at our diagram, big N is acting at the same point as the friction force, because there's, you know, we're assuming there's friction between the ground and the ladder, but not between the wall and the ladder, then we have to use big N here. And so now we have three equations, and we have how many unknowns? Okay, we don't know this. We don't know this. We know the masses, and we don't know this, right? So it looks like we have three equations and three unknowns. Yeah, I don't want want to do the algebra here, but I think I probably will have to. Okay. All right, let's do this then. Let's do the algebra. So from the second equation here, right, we see that this big normal force, this is one of the easier ones to solve for, should just be big mg plus little mg, right? So that's cool. Then if we take that result up here, what we find is mu sub s times big mg plus little mg minus n equals 0, right? And this tells us then that little n is mu sub s g times big M plus little m, right? If we factor out the g and simplify it a bit, okay. So we're kind of getting somewhere. Now we have to take the result that we found for little n and plug it into our torque equation. So nothing about the first two terms here will change. So I'll copy and paste those. Then we have to substitute for this term, right? So we're going to write mu sub s big M plus little m g sine theta equals 0. And we can actually cancel the factor of g because that's everywhere. We could actually go through and divide every term by cosine theta as well, because we can then, let's see, do this. And then, so the first two cosine thetas disappear, this becomes tangent of theta, right? Sine of theta over cosine of theta is tangent theta, and then you just have to solve this for this L here. And I'll leave that for you to do. I think at this point it's very, to use a fancy math term, tractable, right? I think that means just solvable, but I'm not sure. But anyway, so at this point you can go through and get this result without too much difficulty, I think. So hopefully this is helpful and clear. Okay, cool. So let's move on to number 4. This one I don't think is so bad. I will probably use Mathematica here though. We want to say the initial mechanical energy, and we're going to focus just on one of these objects, right? We're going to use this method of just keeping the moment of inertia general, right? We're going to write some variable coefficient in front of the mr squared term, exactly like I told you to do in the problem statement. Though now I don't actually like the fact that I used alpha, because that is what we write for angular acceleration, but just remember that alpha here is not the angular acceleration, right? It's just some fraction, essentially. So, for the initial mechanical energy for one object is just gravitational potential energy, right? So we could write that it is given by mgh, and this is true for every one of these because they all have the same mass, right? Okay, so the final mechanical energy for one object is, and this is going to be the kinetic energy, right? And we have to do the rotational kinetic energy plus the translational kinetic energy. Now let's go through and clean this up. Remember, we're going to say that these moments of inertia are just alpha m r squared. So this is what our rotational kinetic energy term becomes. We don't do anything with the translational. Okay. And then we want to recall, right, that for no slipping, and that's what's happening here, they're rolling down the ramp and not slipping, that we can write V equals R omega. So this tells us that omega equals V over R, right? So we can substitute that in up here, and we have 1/2 alpha m r squared, and then for omega squared we just write v squared over r squared, and then we write plus 1/2 m v squared. Why is this not? Okay, there we go. Then what we find is that in the first term the r's cancel, right? The r squared canceled. R squared zip cancel. So we can write 1/2 alpha m v squared plus 1/2 m v squared. Dimensionally this makes sense, right? Because remember that this is just a number, it doesn't have dimensions or units. So that's, I think, as far as we'll go right now with the final energy, which remember is just the sum of the rotational kinetic energy and the translational kinetic energy. Because these objects are translating, right? Their centers of mass are moving through space, but they're also spinning about their own center of mass. Okay, so we just equate energies now, right? We write E initial equals E final. For E initial, remember we had mg big H. Is that what I called it? Big H? Yeah, good. And then this equals the final energy, right? So far, this is what we have. Then we can actually go through and cancel the m's, which is cool. And we can even factor out the v squared here, right? Or we could do this. We could say gh equals v squared times alpha plus 1 over 2. Actually, I don't want to do that. What I think I want to do is just multiply both sides by 2 to get rid of the 1/2s. Like that, yeah, that's same thing, right? But then we can just write that this is alpha plus 1. Let me just make sure this looks good. Multiply both sides by 2. Factor out the v squared. Yeah, cool. So we finally find, right, that v is going to be the square, excuse me, the square root of 2gh over alpha plus 1. And I can, get into Mathematica now, and wow, this is weird. Like the iPad just made a sound as I opened Mathematica, and I was like what? Mathematica doesn't make sounds. So let's do this. Let's say that we're going to make a function of alpha, right? And I have to put, the underscore doesn't appear, but I have to write an underscore after the alpha to tell Mathematica that this is a function of alpha, and then I write 2 times g times big H over alpha plus 1 under the square root here. And that's my function now, and I can just go through and try the different coefficients, right? So what do we have? We have a solid sphere, so the coefficient would be 2/5. Yes, I had to look at a table of moments of inertia for that. So that is our speed for the sphere. Then we have to do, what was the other object? A hollow sphere. So that should be 2/3, right? Yeah. So that's the final translational speed of the hollow sphere. Then we have to do a cylinder. Now for a cylinder, alpha is 1/2. Or a disk, right? Same thing. So there's that. And then for the, was it a ring or a hoop? Alpha is actually just 1 here, right? Yeah. And so we find this. So you could go through and you see that these all depend on the square root of gh, and then there's some numerical coefficient. Just see which is, which of these is maybe use your calculator, or if I wanted to in Mathematica, I could just tell it to give me a numerical approximation. So for instance, like the first one becomes, we see that the square root of 10 over 7 is just like approximately 1.2, right? And so this is how you would go through, and you would just see which one has the largest speed and which one has the smallest speed at the bottom. Okay, that was a good amount of work, but hopefully everybody is clear on how this was to be done now. Okay, just 2 more problems to go. So let's look at number 5 here. Now, I'll want to make another sketch. And so what I need to do is clear my screen. And let's just draw the free body diagrams for each of the things, right? So for the block M1, the free body diagram is just going to look like this. For the pulley, the diagram will look like this. Okay, there's nobody else in here again. I think I can take this off. And then for the other block, it's going to look like this. This is the block on the right. Okay, so this is like the kind of collection of pictures you want to have in mind as we go through this. And I will now move this off, and we can just do this stuff. So we just want to think about the net force in the y direction on each of the masses. So for each of the masses, or for the masses, I should say, because these expressions will look different. We'll have that the net force on 1 in the y direction is going to be, the tension is going to pull it up, right, whereas the gravitational force pulls it down, and its acceleration will be downward, so I'm going to write -1, or negative m1a here, right? We'll do the same thing for the second mass. This equals T sub 2 minus m2g. This equals m2a. And these accelerations are the same, right? Because these masses are connected by a cord, and so they are constrained to move with the same acceleration. And then the last thing to do is to do the torque, the net torque, about the pulley's axis of rotation, which we'll just take to be the z-axis as usual. Now, coming back to the diagram here, we see that these forces, these tension forces, kind of act tangentially to the radius of the circle, right? It's supposed to be right angle, this is r. And so we don't have to tack on any trig functions when we would write maybe sine, but sine of 90 degrees, right? Remember the angle between the position vector of the force and the force vector is 90 degrees, so that the corresponding torque here should just be r T1, right? And this tension, the one on the left, would tend to make it rotate counterclockwise, so it would be positive. So filling this in, right, what we find is RT1 minus RT2, and this equals, well, the pulley is going to rotate, or is going to start to rotate counterclockwise, so we'll just write I alpha here. Okay, so let's focus on the torque equation. We can factor out an R. Oopsie. and then we can write the moment of inertia for the pulley. And if we model it as a disk, which is what we'll pretty much always do for pulleys, it's going to be 1/2 big M big R squared times alpha. And we see that we can cancel a factor of R from both sides here, which is nice. And then solving for alpha, see that alpha should be 2 times the difference of the tensions divided by the mass of the pulley times its radius, right? Now remember that the no-slip condition gives the tangential linear acceleration is R times alpha, right? So here we can just write that the linear acceleration is this minus, or not minus, but canceling the R, right? Because we multiply this by R and then the R's go away. So we have this now for our acceleration. Okay, so now we know, right? We know what the accelerations are here, and for these equations we have might have done this backwards because we still need the tensions, right, before we can get a number for this. And so let's just do that really quickly. What we see from this one is that T1 equals M1G minus M1A. And what we see from this one is that T2 equals M2G plus M2A. And then we can plug those into this equation, right? And we would have one equation with one unknown, because the only unknown then would be A. And so let's just say we've done that, right? Because that's a lot of algebra, and I don't want to, you know, spend too much time on the sort of less or more trivial parts of this. And so let's assume that we've solved for A and we get some number, whatever it might be. The only thing left to do is to just write out the positions, positons, yes, positions for each mass as a function of time. So we could write, for instance, that y1 for the mass on the left as a function of time is going to be, remembering from kinematics, well, it starts at height lowercase h, yep, and it falls down, right, with this kind of an acceleration. Yeah, and then for the other one, it just starts at y equals 0, and it moves up at 1/2 a t squared. So the last thing to do is just to say, well, at some time, fancy t, the positions are equal. The y positions are equal, right? And so we just say h minus 1/2 a fancy t squared equals 1/2 a fancy t squared. And from this, right, we can just add 1/2 a t squared to both sides, and we just find that h equals 1/2 a fancy t. Sorry, no 1/2, right? Because when we add 1/2 to 1/2, we just get 1. Yeah, and that's it. And so then you would just plug in what we found for A, which would be this. And then you would have to plug in also for the tensions and stuff, and I do think that that's best left to just a computer, right? To do all the algebra quickly and with no mistakes. But this is what you were supposed to do here, right? And notice that the big difference between this example and the ones that we've looked at in the past with pulleys is we just basically didn't have to worry about the pulley, right? We just thought of it as this device that can redirect a tension force as we desire. Whereas now we have to think about its angular acceleration and possibly angular speed if we're talking about a different kind of problem. But this is what you're supposed to do here. Okay, cool. Let's do this last one. I don't think this will be too bad. So for 6, right, for A, the total kinetic energy, remember, is the rotational kinetic energy plus the translational kinetic energy. And most generally, this is going to be 1/2 I omega squared plus 1/2, and I said the mass of the Earth was big M, V squared. So we just need to, really what we need to do is we need to just figure out what omega and what V are. And we're told in the problem statement that we can model the Earth as a perfect sphere, and again, I don't think anybody here thinks the Earth is hollow. Hopefully you're not a hollow Earth conspiracy theorist. So we'll take the moment of inertia of the Earth to just be 2/5 big M little r squared, right? Because we have 2 r's in this problem, so we need to keep them separate. But that's that. So let's solve for omega. Remember that omega is just going to be 2 pi. So remember, this is like 2 pi radians, right? But a radian isn't like a real unit, so we don't have to write it, and we usually won't. Over the, because the Earth is spinning about its own axis, right? And it's going to spin 360 degrees, or 2 pi radians, in some time that is actually 24 hours, like this. And so we can write that omega is simply 2 pi over this little t. Now, of course, you have to convert this little t from hours to seconds, but that's something you can just ask Google about, right? Like, even on the exam, I don't care if you want to use the computer to convert units, you know, that's kind of a small, silly thing, I think, to emphasize or stress about, right? So this is what we find for omega. Let's think about V. Now, V will be, so the Earth, right, has to move through a distance equal to the circumference of its orbit. So we could write this. We could write that the distance in this case is 2 pi big R, where, remember that big R is the radius of the circle through which the Earth travels around the Sun. So there's that. And then the time this takes, right, is 365 days, because it takes the Earth 1 full year to go around the Sun. And so this would be our tangential velocity, or tangential speed here. And again, right, you would have to convert the big R to meters, and you would have to convert the big T to seconds. But I'm not going to worry about that for the reasons we just discussed. So what this gives, right, is that K total, let's fill this in, is 1/2. And then remember, we said we're going to model the Earth as a solid sphere, so 2/5 big M for the Earth's mass, but little r for its radius squared. And then omega squared, right, would just be 2 pi over little t, and then we have to square this. And so you can simplify this, right? You know, just do the algebra. And then we have to account for the translational kinetic energy, which is going to be given by this. And then, and then you would go through, right, and clean this up and make it look nice algebraically, but this is what you should find. Let me just double check this, make sure it looks good. Yeah, I think this is good. So then now that we've gone through and we've done, and notice that this only depends on values we're given in the problem statement, right? Every one of these values is something we are given in the problem statement. And that should be the goal when solving for things. Now, for the total angular momentum, right, we're just going to write that this is the sum of the spin angular momentum, which is the angular momentum that the Earth has because it is spinning about its own axis, plus the orbital angular momentum. And this is the angular momentum that it has because it is orbiting the sun. Now, the spin angular momentum, be careful, okay, because I almost wrote 1/2 I, and it's, remember that the spin angular momentum is just I omega. So don't confuse the expressions for the rotational kinetic energy and the spin angular momentum because they look similar, right? They both depend on I and omega, but one is 1/2 I omega squared. The other is just I omega. And then this, remember, we could write as a scalar. Generally, we said it was RMV sine theta, right? But we're assuming, and this is not the specific form, right? This is just the form that we had from the video. But remember, we're assuming that the Earth moves in a circular path around the sun, which isn't 100% accurate. I think it's more elliptical, but it's pretty good for purposes of approximating. And so this looks like R, no, wait, yes, big R, big M, little v, sine theta, but because it's a circle, sine theta is always sine of 90, and that is always 1, so we can just get rid of this. And all that's left to do, right, is plug in everything. So we said the moment of inertia was 2 big M, big R squared, and omega was 2 pi over little t, and then big R, big M, and then we said that V was 2 pi big R over big T. And then you would want to go through and, clean this up as much as you can algebraically, right? But this is what you should find for the total angular momentum of the Earth. I want to check this too, just to make sure that it looks okay. Pi over T plus Rm, and then V was 2 pi R over big T. I think this looks good. Cool. Okay, so I know I didn't give you the answers, right? But remember that, I don't really give a damn about the answers. I want to see that you understand this stuff and know how to apply it. Like putting things in your calculator or whatever, I just really do not care. As I've said before, this is Physics 174. It's not Calculator Technique 174, right? So just show me that you understand the physics and you don't have to stress so much about the numerical values, okay? So hopefully everybody found this helpful. And if you have any questions as you're studying tonight, feel free to reach out, and I will do my best to help you. All right, that's it. I hope everybody does well on the exam. I don't want to make it too difficult or unpleasant, so hopefully you're not feeling too stressed out, but just do your best. It's going to be okay.